Hello everyone. Today we are going to look at the mathematics behind the CAN architecture. So before we dive deep, let me recap the previous video. If you have not gone through the previous video, I have given the link in the description. Um, in the previous video, we started looking at this paper called Kolmogorov Arnold Networks, and we tried to develop an intuition of the basic concept behind this paper. So let me do a quick recap of that. So we started by discussing about how cans are different than traditional multi-layer perceptrons. And in this slide, you can see we have a traditional MLP where we have weights and biases which are associated with a specific neuron. So what generally happens is that the neuron gets a bunch of inputs which are assigned certain weights and biases, which are added together, and there is an activation function which basically decides whether the neuron should fire or not. Now, what the CAN architecture proposes is that you get rid of the weights and the biases, but you make sure that every connection between two neurons has an activation function which is associated with it. So this activation function is denoted by phi over here, and the activation function is present between any two corresponding neurons. So you have basically got rid of the weights and biases, but you have these functions which you have to train, and these are learnable functions. We also looked at what is the meaning of B spline. So B spline functions are basically used to approximate any function. So basically, there is, if you have any function, you can write it as a series of B spline functions where you can vary the coefficients to match the given function. In order to specify any B spline, you need to mention the number of control points, which are denoted by n plus 1, the order, which is denoted by k. So the number of segments which you will have with this notation is n plus k minus 2. Uh, so it allows you to control each segment separately in the B-spline function approximation. So for example, if we have n equal to 5 and k equal to 3, we get n plus k minus 2 equal to 6, which means that I will have 6 different segments in my curve which I can control separately. You can assume that this is quite similar to the kind of function control we do in CAD or CAM softwares, where you're trying to draw curves by connecting segments. Remember, we try to control each point separately, and the curve between these points changes if you have used any one of these tools before. Anyways, the basis functions typically look like this, which is shown in this figure. Here I have shown five basis functions. Two are shown in blue, two are shown in red, and one is shown in yellow. You can see that the blue basis functions and the red are mirror images of each other, and there is one basis function which goes through the center. So typically we do a linear combination of these basis functions to represent the spline function between any two neurons. Now, the Kolmogorov Arnold theorem basically says that uh, you give me any function, and I will give you uh, uh, basically a two-layer architecture of Kolmogorov Arnold networks, which can be used to represent that function. Now, the problem with this is that if the function is not smooth, you would not get such an approximation, and this was what was the reason why the field was stuck 50 60 years back. Even after the Kolmogorov Arnold theorem was present, it could not be successfully applied to a universal function approximator. What these guys are basically saying is that we can extend the Kolmogorov Arnold theorem and uh, apply it to build neural network architecture of arbitrary width and arbitrary depths so that it can be used as a function approximator. The objective of today's video is to help you understand the mathematics of the CAN architecture. So let's dive deep into the paper now. Okay, so let's look at the KAN architecture, and let's start by looking at some notations. So, okay, so the first notation that we'll be utilizing is phi over here. This particular notation is what we'll be looking at first. So these are one dimensional functions, and uh, between two layers. So Q is representing one layer, and P is representing the second layer. So basically, you can assume them to be one dimensional functions between two layers, two corresponding layers. The first layer has n in number of neurons. The second layer has n out number of neurons. Uh, so uh, let's try to look at it in terms of the original Kolmogorov Arnold theorem. So in the original theorem, what they basically said is that if you have n neurons in this layer, the second layer will have 2n plus 1 neurons, and the final layer would have one neuron, basically, which is what you see in this formula over here. Q goes from 1 to 2n plus 1. Okay, so the n in, according to our notation, over here is n, and the n out, which is the number of neurons in the next layer, is 2n plus 1. N out is 2n plus 1. Okay, so that is what they are saying over here. In the Kolmogorov Arnold theorem, the inner functions form a CAN layer with n in equal to n, and n out is equal to 2n plus 1. And the outer functions form a CAN layer with n in equal to 2n plus 1 and n out equal to 1. So basically, what this means is that, let's say we consider this for these two layers, n in is n and n out is 2n plus 1. But for these two layers, the output in the first case becomes the input. So the n in is 2n plus 1, and the n out is equal to 1. So this is what the notation essentially means. Let us draw it separately over here, so that go from 2, then 5, and then finally 1. Okay, okay, so let's move ahead. So the shape of the can is typically going to be represented by this integer array n0, n1 up to nl. And so if we are looking at this particular can, then we are going to represent it. It's a three layer can, so l equal to 3, and n0 is 2, n1 is 5, and then it's 1. So this is the three layer network which is represented according to our notation. Just keep this in mind. It is just as a symbolic notation. It will not hinder you in your understanding of the algorithm that much. Okay, so let's go to the next step now. Okay, so we denote the ith neuron in the lth layer by Li, and the activation value of the Li neuron by XLI. So between layer L and layer L plus 1, there are NL into NL plus 1 activation functions. Okay, so let's try to first understand this. This is also quite simple. So they are denoting the layers by L. So if this is the Lth layer and this is the L plus 1th layer, then this particular layer is going to have NL number of neurons, and this particular layer is going to have NL plus 1 number of neurons. So can you guess the number of activation functions? It goes from each neuron in the first layer to each neuron in the next layer. So it is going to be basically, let's say you consider this has 1 2 3 4 5, this has 1 2 3 4 5. So 5 plus 5 10. You can also write it as 2 into 5. So it's going to be NL into NL plus 1. These are the number of activation functions that you have uh, between layer L and layer L plus 1. That is what it is basically saying. And the input at this layer is given by this notation XLI. So okay, so basically this is the ith neuron in the Lth layer. So let's say L equal to 0 here. So this will be X00, which is the first neuron in the uh, so the notation, if I'm not wrong, is XLI. Okay, so where L starts from 0. So XLI. So this is going to be X00 and this is going to be X01. Similarly, this here L becomes 1. So this is going to be X11. Uh, sorry, X10, X11, X12, X13, X14, etc. And then this is going to be X20. So this is how the labeling of the individual neurons is being done. It has two indices basically. The first index denotes the layer, and the second index denotes the position of the particular neuron within that layer. Okay, so let's move ahead now. Okay, so now that we have defined the notations for the layers and the notations for the individual neurons within that layer, uh, we are going to look at how can we define the activation functions that connect uh, the neurons in the corresponding layers. So the activation function, as I was previously also mentioning, is denoted by the function phi. So let's say we are talking about layer L, and we are connecting the neurons in Li and L plus 1j. So the activation function is given by phi L ji. So what do I mean by that? Let's say let's say you have these layers. You are talking about 2, 3, 4, 5, and then this is layer L, and this is layer L plus 1. So the activation function is basically given by phi uh, L, J, and I. So why do we have three indices? The first index basically denotes which layer is it going from. The second index denotes the first neuron, and the third index denotes the second neuron. So basically here, if we have the activation function like this, then it will be phi L 00, and if I have the activation function like this, then it will be phi L10. Remember that the second index is the layer which is the next layer, and the third index is the starting point of the connection for which the activation function is connected. And now let's what's the range for this L? L goes from 0 to capital L, I guess. It's where capital L is the number of layers. Then what does j go from, what does I go from? So uh, I goes from 1 to nl, and j goes from 1 to nl plus 1, where nl and nl plus 1 are the number of neurons in that particular layer. And L goes from 0 to capital L minus 1, since capital L denotes the number of layers. Okay, so I hope this notation is very much clear up until this point. Now let's try to understand how can we represent an overall function. So basically, we would like to define a matrix now. Now it's really interesting how do we go about doing that. So okay, so I'll again have a new page. So let's assume that we have this network over here, 5 and 1. Okay, so now we are going to look at how can we create a matrix out of this. Okay, so now let's see that let's say that you would like to understand what's going as the output from this. So what do I mean by that? So let's say so this we are denoting by x00, because it's the 0th layer, and x01. Someone asks you the question, what is the value of x10, which is this neuron? So what will you do? You will take x00, you will multiply it by phi 0, then phi 0. So let me try to get a sense of. Okay, so I and j start from 1, right? So phi 0, then 1 comma 1, which will be this. And now I want to represent this, which is plus x 0 1 phi 0 comma uh, so 0 is the layer and 1 is the neuron where it's going to, which is the same, and then 0 comma 1 comma 2. So this is how I'm going to represent it. Similarly, what about this? This I will represent by x00 phi. The layer remains the same, of course, but this now changes. It becomes 2 phi to 1 plus x01 phi 0 to 2, etc. Now, if you think about it, this looks like I'm multiplying two vectors together, which can, of course, be represented as so the first line can be represented as a matrix x00 x01 times phi 011 phi 012. Similarly, we can do the same with the second one also. So you can append it at this, basically remains the same. And here you have x021, sorry, phi 021 phi 022. So what you have done is that you have represented these x's by multiplication of the original layer into a matrix of functions. Now this is exactly what they are doing over here. They have represented this matrix of function like this, and this is xl, and which is the input, and xl plus 1 is the output, which is exactly what we did in our example. So this matrix is denoted by a symbol which is bold phi of L. So this matrix is denoted by this symbol, bold phi of L. And basically it depends on the layer. It does not depend on the position of the neuron at all. And this is a collection of all these matrices at the different layers. So in essence, what you can do is that phi 0 phi 1 phi 2 phi 3, you can represent the entire can like this. You can represent the entire can as, let's say, this is the input. Input is x. I'll write it at the end. Then you can do phi L minus 1, phi L minus 2, dot dot dot, phi 1, phi 0, and then you multiply it by the input. That's it. So this is that simple. So whenever you read this research paper, don't get too bogged down by the architecture and the mathematical notation. It is really very simple, as I have outlined the details of the architecture to you. So this is in essence the mathematics of uh, the CAN architecture. The difference between MLP and can now also be specified in terms of this functional notation. In MLPs, we had these weight matrices, and now these weight matrices and the activation functions have together been replaced by this single matrix phi, which is another neat way of explaining to someone what is the difference between MLPs and CANs. Now, you might be wondering, how do we mathematically represent these phi functions which are appearing between any two consecutive layers? So it is basically given by this formula, where it's not really necessary to have w outside. You can absorb it in the functions, where b is a constant function which is given by the CLU function, and these are the most important functions which I explained at the beginning of this video. These are called as b spline functions, where they are given as a linear combination of ci's into bix, which are the functions, the b spline functions, and these are trainable. So you basically fix BIs and you basically train these CIs so that it matches the function that you are looking at. So this brings us to the end of today's video, in which we looked at the mathematical notation behind cans. If you have any doubts, feel free to post in the comment section, and in the next lecture we'll be going through some more aspects of Kolmogorov Arnold networks in detail. Thank you.